was going to talk about branching programs, putting lower bounds on branching programs, and there our best lower bound is like n log squared n, and actually this lower bound easily implies that lower bound. So any branching program you can easily simulate with such a circuit very efficiently, and this lower bound proves that this function cannot be computed with, say, a constant width branching program of length n log squared n. And that's been a problem that's been open for a long time. So if you could somehow improve this to log cube n, you'd be solving some old problems from the 80s that people thought about a lot.
Can you say just a few words? What are the tools to prove this lower bound?
It's very interesting. So this is actually a setting where information has not managed to penetrate. Okay, so the tools are discrepancy. So what you do is you study so you know that if you have a low communication protocol, there will be a large monochromatic rectangle. So what you try and do, if for two parties, what you can try and do is show that every rectangle is close to balanced. Okay, the function is close to balanced inside it. That will prove a lower bound. And that's the kind of tool that works here. So corresponding to rectangles in the number of the forehead model, there's a concept called a cylinder intersection, which is what you get when you fix the communication of the protocol. And you try and show that every cylinder intersection is balanced. And you can do that by analysis, basically. It's essentially Cauchy-Schwarz, repeated applications of Cauchy-Schwarz and convexity. Okay, so welcome back. I will continue by quickly telling you something about distributed algorithms. Hopefully this will be fast. And I just want to tell it to you because it also uses this lower bound on the number one forehead communication complexity of disjointness. And then I'll switch to talking about data structures, and I probably will not get to polytopes today. Which is sad because that's some exciting work. Okay, so Stefan on Friday told us of a few distributed problems where you can prove lower bounds using reductions to communication complexity. And here I want to tell you about another one. So the problem I want to talk about is you have a distributed network. So the setting is you have n players. And each one, they're connected by a network. And the network is, say, an undirected graph. So this player can talk to this player back and forth. But they kind of don't really know the whole network. Okay? So each player only knows who his friends are. He doesn't know how many, how the rest of the graph looks at all. And a thing that people study in distributed algorithms a lot is how can you, start to communicate over a network, or how can you even compute basic features of this graph? Like maybe you want to compute a spanning tree of this graph, so you can use it to route messages. That's what Stefan talked about. But today I want to talk about the problem of just checking whether or not the graph has a triangle. Okay? Seems like a pretty simple problem. So you know all your neighbors, and the question that you want to ask is, does the graph have a 3-cycle? And I realize I'm forgetting one of the authors, but OK. So the theorem I want to prove, which is proved by Drucker, Oshman, and unfortunately I'm forgetting, I think there's another author whose name I forget. My apologies. My apologies, mysterious author. But what they proved is that this task cannot be solved unless the total communication that takes place, the total communication so here there are n vertices, must be at least an expression that looks like n squared over 2 to the square root log n.
So the graph is given, it's a bunch of players, each one owns a node, the node is edges?
The edges are part of the input. So you want an algorithm that will work no matter how the graph is arranged.
Right,
And
each node is a person,
yeah.
is a player, and his input is which edges he owns. He
Yes.
calculates mountain,
Yeah.
and we together want to compute whether there's a triangle.
Yes.
So the trivial thing is sending all neighbors as n squared.
Yeah, if you announce all your neighbors, that will take n squared communication. And this shows that you cannot do much. You can do maybe you can do a little better than that, but you can't save more than a 2 to the square root log n factor.
And also the model is just everybody announces, so there is not.
Yeah. Yeah, I'm going to prove a lower bound, so I allow them to do even just announce. So actually, what people care about distributed computing is they communicate.
Announcing one bit is just one bit of communication.
Yes. Yeah. So usually they care when they care about much more restricted models where they're only allowed to communicate along the links. That's what makes sense for the upper bounds. But the lower bound I'm going to prove is even if they're just allowed to send everybody a bit. Let's see the lower bound. So far there's no communication, it's just a graph. But now I'm going to relate it to number on the forehead. Okay? What I'm going to relate it to is just 3-party disjointness. So k will be 3. And then I know there's a lower bound of n here. But what I'll first do is, it's taking way longer than I expected, as usual. So first I'll explain the lemma, which I won't prove, but that's where the strange 2 to the square root log n comes from. Actually, I'll tell you something about the proof. So one fact that's interesting is that there is a subset of the numbers 1 through n whose size is n over 2 to the square root log n. And S has no, I'll write theorem here. So the theorem of Barron, and S has no 3-term, or it has no arithmetic progression, has no non-trivial arithmetic progression. Okay, so arithmetic progression is like 5, 10, 15. That's an arithmetic progression. So this is a problem that was studied for a long time in combinatorics. But there's a set which is pretty large, has n over 2 to the square log n numbers in it from 1 through n, but it avoids all 3-term progressions, or avoids all progressions. So why is that useful? It turns out, and this is, you can try to do it yourself. It's an exercise. This means that there's a graph. There's a graph which is tripartite. Okay. So it's going to have n vertices here, n vertices here, n vertices here, and it's tripartite. So all the edges go like this. Okay. And this graph will have n squared over 2 to the square root log n triangles. And moreover, every edge is in a unique triangle. Okay, that's a claim. So I'll just give you a hint about how to construct the graph. So what you do is you connect A and B here if their difference b minus a is in the set S. So that's my hint for just this edge. And then I will let you decide how to connect the others. Okay. So let me just sketch how this reduction works. So here's the idea. So say we're in the number on the forehead model and there are 3 parties. Okay. So there's Alice, who has x sub a, Bob, who has x sub b, and Charlie, who has x sub c. What they're going to do is they're going to interpret their sets as being a subset on the universe of all triangles in this graph. Okay? So every triangle is a potential element in the universe. And Alice has a set of triangles, Bob has a set of triangles, and Charlie has a set of triangles. And then the idea is, suppose, so each of these sets is going to be related to Alice, Bob, and Charlie. So suppose Alice controls this, Bob controls this, and Charlie controls this. Then what they're going to do is they will add an edge here. This edge will be included exactly if the corresponding triangle is in Charlie's set. Okay? So this edge, there's a one-to-one correspondence between the triangles and the edges in this graph. Okay? You can go back and forth between them. And the way we'll construct the input to the distributed algorithm, so Alice, Bob, and Charlie get their 3 sets. And what they're going to do is those 3 sets are going to correspond to a graph, a subgraph of this graph, which is obtained by this process. So you include this edge between Alice and Bob if and only if the corresponding triangle is on Charlie's head.
What is the corresponding triangle?
Because the lemma says every edge is contained in a unique triangle.
Every edge.
Okay? That's the non-trivial thing about this graph. So this edge is contained in some unique triangle in the space of triangles. So you look at whether that triangle is on Charlie's head. If it's there, they include it. Now, they can do this in their heads without communicating because they both see Charlie's forehead. Okay? So what happens at the end of this process is Bob knows all of the edges that touch this thing because he knows Charlie's forehead and he knows Alice's forehead. Okay? So Bob knows all the inputs to these players. In the same way, Charlie knows all the inputs to these players and Alice knows all the inputs to these players. So now they can simulate the distributed algorithm and they find out if there's a triangle in the graph. And when is there a triangle, it means that triangle must be in all 3 sets because all 3 edges have to be all 3 edges of the triangle have to be in. So it's kind of a nice idea. But it shows that, so that means the communication, the number of triangles here was like n squared over log 2 to the squared log n. And the communication must be at least that much. Okay, so that's another reduction.
Is there any non-trivial algorithm?
Not that I know of.
The non-trivial upper bound will give you an upper bound on the size of sets without arithmetic progressions.
No. You can prove an upper bound without violating this, without proving an upper bound in this lemma, right?
No, like.
Because this lower bound will always.
Yes.
Yeah, you're right. So any stronger, yeah.
So any
Yeah.
upper bound for this problem will solve any problem.
Any upper bound will solve the arithmetic progression. Yeah. That's a good point. Yeah.
Why it's not known that the arithmetic progression bound is tight?
Yeah, this actually is a famous open problem in combinatorics is whether this is tight. The best upper bound looks like 2 to the log n. Is that right, Clem? Or,
I think n over log n.
oh, n over log n, which is 2 to the log, same. Okay. All right, so next I want to, once again, the model will change, the communication will stay the same. And I want to talk about data structures. And now I'm going to go back to just two-party communication. So again, there are a number of problems you can study in data structures, but I'll focus on one question that people care a lot about, and that's the question of efficient static data structures. So, so what's an example of a problem? Let's just start with an example to understand what kind of problem we want to solve here. So the setup is we have some input that we want to somehow pre-process and store in a data structure in such a way that you can ask queries very efficiently of the data. Okay? So for example, suppose you want to store, so I have a graph G, an undirected graph G. And I want to somehow process this and store it in a data structure of size S. So I want to store like S bits. And usually in these models, they have like a word size. So you kind of think of like S words, each of size log n. And then at runtime, what's going to happen is you're going to need to answer queries of, that look like this. Is UV connected? So is U connected to V? Okay. So I want to store the data in such a way that I'll be able to very quickly check whether U is connected to V. So the naive thing you could do is just store a n by n table, n squared bits that say for every pair UV are U and V connected, but that's n squared bits. Does someone see?
We assume about G somehow. Why it's going to be compressed?
No, this is nothing. We don't assume anything about G. Okay, but let me say. So I didn't say exactly what we care about. So what we care about is we want to minimize S, and we also want to minimize the running time of the algorithm. Okay, so we want to minimize also T, the number of queries you need to make to the data structure to answer this question. Okay. S is a parameter. So we want to minimize both S and T. Okay. So the trivial idea that I talked about would have S equals n squared, and T would be 1. Okay. Just look at one position. Does someone see how to do it with S that's closer to n?
If G is arbitrary, there is n squared possible H's. So how can you compress it to more?
You'll find out in a second. Okay, you could store the graph, but that's even worse than the idea that I talked about. That's even worse than the idea that I talked about, because you're storing n squared and still storing t. The point is, Sasha, you don't need to store the whole graph. You just need to understand this question: is U connected to V? So you can forget about information that's irrelevant to this question, right? Like if there are two paths between U and V, maybe you can forget about one of them.
Oh, so what you want to just equivalence relation.
So
you just keep the number of the component.
yeah, exactly. So you just store, for every vertex, you just store a table that says the name of its connected component. Okay? So just the name of the connected component, and then to check if U and V are connected, you just need to check whether they're in the same connected component. So that's, query log n, log n length word for U, and log n length word for V, and this tells you whether they're connected. And now S has become like n words, and the running time is 2. Okay, so you see that there. Okay, so that's the basic setup. Okay, we want to understand for natural problems what is the trade-off between S and T. Okay, you allow a big pre-processing time, but at a runtime you want very fast access. Yeah, we don't pay for the pre-processing. Yeah.
So sorry, can you repeat so your suggestion? Still, when you read the number of queries, each time you read a query, you get like, I mean, what's the size of what you read when you ask a query?
This is a parameter that I don't want to make the model complicated, but usually they assume that you can read, their log n size words.
Okay, so you have your, let's say, okay, so you have your components, you write your components.
Yeah.
But some components can be very large, right? So how
Yeah.
do you,
It doesn't matter. You label, you call component number 1, and every vertex that's in that component, you give it a label of 1. So the label is only.
I see. So you have n. Which
Yeah. So this is going to be a vector of length n,
I see.
and each one. Yeah. And that's the best you can do. It's easy to see here. But okay. So this is a setup. So we have 2 parameters S and T, and we want to understand the trade-off between them. And so let me show you. First I forgot. So to understand this, it turns out, we'll see in a second how we do the reduction, but it turns out Alice and Bob are not going to play a symmetric role. So there's a connection between the communication world and the data structure world, but the connection is that Bob is going to somehow simulate storing the data structure, and Alice is going to simulate running the algorithm. Okay, so they're going to play 2 different roles. And for that reason, we need to understand so-called lopsided problems, and one of which is the lopsided disjointness problem. So let me tell you the problem. So X is going to have a set of size n, a set, and Bob is going to have a set, just as before. But now X is going to have a special format. X is going to look like this. So it's going to be, so this is the indicator vector for X. And there are going to be k blocks here, k blocks. And in each block, X will have exactly 1, 1. Okay, so this means the size of X is going to be k. Okay, which we think of k as much smaller than n. And Bob has, as before, an arbitrary set. So the problem is lopsided because Alice has a small set. It just has k elements, which means, for example, the trivial protocol here is Alice should just send her set, right? Because that takes k log n bits of communication. And we'll show that what you can show in analogy with the old proofs for disjointness is that that trivial protocol is essentially tight, in the sense that, let me find the bound. So a theorem you can prove. So if Alice sends A bits and Bob sends B bits, so I should say this is a result of Milterson, Nissan, Safra, and Wigderson. Then it must be true that A plus B, so you get a strange expression. It's at least n over 2 to the A over k plus 1. Okay, so actually, so let me explain that bound a little more. So one way to interpret that bound is that either B is at least, so one consequence of that bound that I'll keep using is that either B is at least of size, at least B is like square root of n times k, or A must be of size half k log n over k.
So, sorry, you saying that n plus k is greater than n over 2 to the what? What's the problem there?
A over k
A over k.
plus 1. Okay, so it's a computation, we won't do it, but this is the form that I'll use. Okay, so just this has a natural, at least this quantity has a natural interpretation because this is roughly, this looks like n choose k, log of n choose k. Okay, so you know the trivial protocol we talked about, Alice would have to send log of n choose k bits to describe her set, and it's saying essentially either Alice does that, or Bob has to send way more bits. Bob has to send like square n times k bits. Okay. So that's a nice bound, and let's see what it says about data structures. So first, I'm going to use that bound just to illustrate the ideas to prove a lower bound or maybe a problem that's not so natural, but it'll be simple. And then I'm going to use the bound to prove a lower bound on a problem that's very natural, but the proof will be complicated. Let me just make sure that what I said can hold. Okay. So let's consider now a specific problem. Actually, the problem will be pretty much the lopsided problem. So maybe this problem is. So here's the problem. So imagine that we get the set y, and we want to preprocess y. So imagine that the data structure problem is you start with y, and you want to preprocess it into a string of length s. And then the algorithm gets x. Okay, so A gets x and starts making queries into this string. Okay, and the algorithm is supposed to answer whether or not x and y are disjoint. Now it kind of makes sense that x is smaller than y, right? So you think of like you have a huge set that you want to store, and then at runtime you're going to get a very small set, and you just want to check on these few elements whether there's an intersection with this big set that you stored. Okay, so like a very special case of this setup is when k equals 1, and that was actually already a problem where there's something interesting you can say. So that's just the dictionary problem. You just want to store a set and know at runtime if an element that you have is in the set. Okay, it's a natural problem. So what I'm going to show you is that, so here's the theorem. Either t is at least square root n times k, or s is at least n over k to the power k over t. So that's the theorem. So if you have any data structure that solves this problem, either it makes lots of queries, like square root n. Yeah. So they want to know, the algorithm wants to know this question. Okay, and again, so this parameter here, just to explain, so this is approximately, well, all of these are approximate, but this is n choose k power 1 over t.
Can algorithms be wrong sometimes?
Huh?
Can algorithms be wrong sometimes, or it should be given correct answer?
Here it should be correct all the time. If I want to allow the algorithm to be wrong, then I need to prove a randomized lower bound on the communication, which we also know how to do, but I won't describe that. Okay, so just so we understand these parameters, so if t is equal to 1, this says that essentially all you can store in the data structure is the trivial thing. The trivial thing is for every possible set x, you store whether or not x and y are disjoint or not. Right? That's the trivial thing. And it says this describes how the thing should trade off as you allow more queries from the algorithm. Okay, so what's the reduction? So, as usual, I'm going to show that if you want to solve this problem and you have an efficient data structure, one that violates its parameters, then you're going to get a too efficient solution to this problem. So what's the reduction? So Alice is going to have x, and Bob has y. Alice is just going to simulate the query algorithm. Okay, and to simulate the query, so Bob can compute this data structure. So Bob does that. Bob now has this s-bit string. And in the first step of the query algorithm, Alice wants to read one of the bits. So she just needs to send Bob a message saying which bit she wants to read. Okay, so in the first round, she will just send log s bits to say which bit she wants to read. Okay, and then Bob will respond with the value of the bit. Okay, so a word, one word. And then this is the algorithm. So there will be t rounds of interaction, and in every round of interaction, Alice will send log s bits to describe where the algorithm is making the next query. And then Bob will respond with the contents of the data structure at that query. Okay? So if you do this reduction, and you have such a data structure, then you get that Alice's total communication, it's at most t times log s. Right? There are t rounds where she sent log s bits. And Bob's communication, it's at most t. Or actually, if the word size is w, it's t times w. But let's just say t for now. Okay, and that's exactly what this translating this condition via those relations gives you this bound. Because, so what this says is that either, so what we know is that either, from the lower bound and lopsided disjointness, we know that either b exceeds square root nk, in which case t exceeds square root nk, or a has to be at least half k log n over k, which is exactly the bound that we got. Which implies that t log s is at least half k log n over k. And that's the same as saying that s is at least n over k to the power k times t, k over t. Yep.
So what kind of questions in Anup with the data structure, that data structure thing? They study their kind of specific questions, like they do like computation complexity. They often study I guess, but invariance of it. They take specific problems and they fill them until they find this answer. Is it similar to the data structure thing?
It is, yeah. So the question that received a lot of work, which I won't talk about today, is nearest neighbor search. So you imagine that you have endpoints in space. You want to store them in such a way that at runtime, you get a new point and you want to know which of the endpoints is the closest. And you can answer that query quickly. And then there are other graph problems that are studied, like things like maintaining the median is one thing that's still, there are no lower bounds. There are results in a slightly different model where it's really interesting to still maintain a graph. This is to handle connectivity queries. That's something that's useful in algorithms, and it's interesting to understand how cost effective that is. But the next maybe this looked like it was missing some meat, like it's the same problem. Let me show you now something that's a little more surprising, and maybe the problem is a little more natural, unless there are other questions or comments. So let's now go back to graphs. Okay, so we solved this problem here. Here, right? There's this solution. That was nice. So let's try and see what else we can do with graphs. Actually, I want to stick with connectivity, But now I want to talk about directed graphs. So let's say G is a directed graph. And again, I want to somehow process G, store an S long vector that has log n size words, say. Okay, so I allow you the same thing that happened for that upper bound. And now again, I want to ask, is there a path? Is there a path from U to V? This is what I want to ask. Is there a path from U to V in this directed graph? So, if you allow just one query, it's easy to see that you can't do anything interesting. You need to store n squared bits of information. And with n squared bits of information, you can do it because your graph could look like this. It could be, it could be a graph where all the edges go from left to right. Okay, and there are n over 2 vertices here, n over 2 vertices here. And then basically, you basically need to store every edge. Because for every combination, you need to know whether there's an edge from U to V. So that's all you can do. So there's no way to sort of shrink this question. But the question becomes interesting when you talk about sparse graphs. Okay. So I promise you ahead of time that the graph is sparse. Every vertex has only a few neighbors. And then I want to be able to do this. Okay. And there it's not so easy to prove a lower bound. Actually, I'm not sure if there's a non-trivial upper bound either. But what I'm going to do is show you a lower bound even for sparse graphs. Okay, so is the problem clear? Okay. So the theorem I'm going to prove is due to Petrascu. So the theorem. So for the purpose of this theorem, what sparse is going to mean is that there are going to be only roughly n log n edges. Okay. So every vertex on average will have only log n neighbors. Nevertheless, what you can show is that any solution to this problem must store a superlinear. Well, so what you can show is that either T. So actually the bound is just like this. It says T is omega log n divided by log S over n. Okay. Okay, which means, so this is the bound that you can show. Petrascu. And in particular, it means that if T is a constant, if T is order 1, then S, I claim, must be superlinear. It must be like n to the power 1 to omega 1 plus omega 1. Okay, because if T is a constant, that means this bottom term has to look like log n. And the only way that can happen, you have to have S log squared n divided by n has to be polynomial in n. So that means S better have some kind of polynomial advantage over n. Okay. Okay, and this reduction is a little more interesting. But we're going to again reduce from the lopsided disjointness problem. So as usual, I'm going to construct some gadget, some hard type of graph, and then try to show how it can be used to solve the disjointness problem. Okay, so let me describe the hard graph, or the hard family of graphs. So the hard graph is going to be a subgraph of the butterfly graph, okay, which is a sparse graph that has some very nice properties. So what is that graph? So we will set, so I'm going to introduce two new parameters. B is going to be approximately log squared n, and D is going to be approximately log n over log n. Okay, and then the graph is going to be a layered graph, where in each layer is identified with the set B to the power D. Okay. Does it make sense? Okay. Yeah. So each layer is going to be identified with this set. Okay. So we're working with the alphabet 1 through B and taking D tuples in that set. And they're going to be D layers. Okay. And all the edges will go from one layer to the next. Okay, and they'll all be directed downwards. Okay. So now let me describe how the reduction works. So in this graph, so to describe the edges, let's look at a particular vertex. So suppose you have U that's in B to the D, that's in one of these layers. Then I'm going to write U minus I. So say, okay, U minus I is going to be the string that looks like this. So it's going to be equal to U everywhere except in the ith coordinate where I'll put a star. Okay. And in the ith layer here, the way this graph is structured, I only connect a vertex. I connect every vertex here, U and V, if and only if U minus I is equal to V minus I. Okay? So I only connect vertices that disagree in the ith coordinate. If they disagree anywhere else, then I don't connect them.
If they agree.
No, if they disagree in the ith coordinate, which means, I only connect them if they agree in all coordinates that are other than the ith coordinate. The equation said it better than. Okay, so that's all the graphs I'm going to construct are going to be subgraphs of this graph. Okay. Now, how to do the reduction? So just like before, Alice gets a set X, Bob gets a set Y. The way the reduction is going to work is that Alice is going to, the universe here is going to be okay, so the universe, so X and Y will both be subsets of a universe that's of size D times B to the D minus 1. B to the B to the D. Okay? And Y is also going to be a subset universe of the same size. And now I'll tell you what the universe is. So the way we'll interpret x is going to be, we're going to think of x as storing for every u minus I, x will have an element x sub u minus I. That's a number from 1 through b. Okay. And y is going to have a subset from 1 through b. So, okay, so let me go back to this picture and try to explain what's going on. So Alice and Bob are supposed to get sets that look like this. Alice has one element out of every block here. And in this reduction, the size of each block is going to be b. Okay? And the number of coordinates is exactly the number of strings u minus I that you can have. Okay? So the number of blocks is exactly, so each block corresponds to u minus I for some u. And this element, which is from 1 through b, Alice interprets that as an element of the numbers from 1 through b. And Bob, for each block, has an arbitrary subset of 1 through b. Okay, so Bob has, for each u minus I, a subset of 1 through b. Okay, so that's now I moved from, once they have sets, they decode these values. For every u minus I, Alice decodes a number, and Bob decodes a set.
So I think of each u minus I as a three-dimensional vector, not u minus 1. I mean, the x there has a purpose.
It is a d-dimensional. I mean, there's a star. One of the dimensions is forced to be a star. Yeah. So now let me tell you Alice's graph. Okay. So the whole point of this is that, well, it's a clever construction. There are many points, but we're going to somehow take the set and use it to find a subgraph here. And the subgraph is, for the proof you'll see, has to have a very special property. The property is that it should consist of many sort of edge disjoint paths that go from the top to the bottom. Okay, so we'll always guarantee that Alice's graph will look like many disjoint paths from the top to the bottom. And the way we'll do that is Alice will construct a graph where, so Alice will connect in this graph, u minus I, in the ith layer, there can be an edge from u minus I only to v minus I, but she'll connect u minus I will have an edge exactly to ui will be connected to exactly vi to the vertex ui so u will be connected exactly if u minus I equals v minus I and ui is equal to vi is equal to it's easier to explain it in pictures, but I'll write it first. Ui plus x sub u minus I. Okay. All right. So Alice is trying to decide whether u and v should be connected or not in her graph. And to do that, she'll look at the corresponding entry u minus I. And u and v disagree only in the ith coordinate. She'll make sure that the difference between those two numbers is exactly the entry that she has, x sub u minus I. Okay, so, or maybe here I need to write mod b or something. Okay, so the difference between the ith coordinate here has to be equal to the value that Alice has. So what we're defining here between all the vertices that have this value of u minus I is a matching. Okay, and the matching corresponds to the number that Alice has. So in fact, the entire graph in this layer is a matching for Alice. And that means that the entire graph here looks like edge disjoint paths from top to bottom. Okay. So I'll just describe Bob's. We're almost done. So what Bob will do exactly the same, except, she will connect u minus I equals v, only those that are equal, and she'll only connect them if vi minus ui is not in her set. Okay, so that's Bob's graph. And the point is, so basically, if there's an intersection between Alice and Bob, that means there's some edge that Alice has that Bob deleted. Okay? This is the crucial point of this construction. There's some edge that Alice has that Bob deleted. Alice has a whole bunch of edge disjoint paths, and there's an intersection exactly when one of Alice's edges was deleted by Bob. Okay? And that means that if you take the starting points here, so what Alice will do now to compute whether or not there was an intersection, she will take the starting points here, and she will follow her edge disjoint paths to the end. She will look at the ending points, and she will ask k queries that are sort of, is this connected to its ending point? Is this connected to its ending point? She'll ask all of them in parallel. And if one of the edges that she had was deleted, one of those connectivity queries will return, no, they're not connected in Bob's graph. Okay, that's the feature of the construction. I guess there are details here that I didn't have time to get to. Okay, but what's clever about this is that what he does to prove the lower bound, to get those bounds, is he needs to do queries in parallel. So unlike the previous reduction where we were doing doing one execution of the algorithm, now he'll do k executions in parallel, and he'll use the fact that so in each step Alice will send. It's roughly the size of this. Actually, it's b to the d minus 1. It's a number of equivalence classes on the top. Okay, and for each one, you'll generate a query, and you can do them in parallel. If you have a data structure, you can do them in parallel very efficiently because you kind of, to specify, so in the first step, Alice is going to do the first query of all k executions of the algorithm, which will require looking at k different coordinates in this space, and that takes log of s choose k bits to communicate to Bob. Okay, and somehow, we're very far from seeing why that's true, but it turns out, this is smaller in general than k log s, right? It's actually closer to k log s over k, and that over k is what gives us lower bound. Okay, so somehow doing this in parallel wins something, because you're able to send these better than doing them independently. So I won't do the calculation, but it eventually gives this lower bound. Okay, so I'll stop there.